Good afternoon. Hi, everyone. Nice to see you again, as always, as is the case for every single lecture. Um, Hope you're having a good week. Hope lockdown's treating you okay. I can imagine that some of you probably aren't having a great time for various reasons, but I do hope your day is going well. Um, I haven't gone crazy yet, which is a good sign. So hopefully none of you have gone crazy. Though, there's still a week and a bit left, right? There's like 9 days left. So, let's not talk about boring things. Let's talk about fun things. Let's get into the next topic. So, bit of a recap for those who watch these lectures live. We just did the ADT and then the implementations on Tuesday. So we essentially learned about like what is a graph, what's the interface of a graph, and then what are different ways we can implement it, and what are the trade-offs. Since then, I have actually gone and updated these slides. I've added a few things in like search. I think there were a couple of typos in here. But yeah, I just added a few little details that we talked about in the previous lecture. Waleed says, a small question before we start. How do we practice the theory in the course? We can search up leak code questions to practice the practical part, but the theory questions are a bit hard to find. That's a good question. I mean, to be honest with you, like if you wanted to practice a lot of the theory in the course, and I guess by theory we mean like kind of like pseudocode and algorithms, I would probably go practice it practically. Like, there's some topics that we don't go into extensive depth in, like say 2, 3, 4 trees. But you could go and implement a 2, 3, 4 tree, for instance. That would probably be the best way to, I think, practice it. Yeah, there is a textbook somewhere. I can't remember where it's listed. So it didn't help? No, I'll try and I think it might have been in the first lecture. I can't remember. I genuinely can't remember where it is. I will try and... There it is. Yeah, here we go. You can go and have a look at this as well. There is a textbook. It's in the course outline as well. It's in the lectures. That's definitely a good way to do it. This covers a lot of things. Sorting, searching, data structures, some of the key things about algorithms. So that'd be good. Though I do think just trying to apply a lot of theory helps you understand it. Most of the theory that we teach that I understand the best is when I've had to go and solve a problem with it. So I think that's always a good start. Yeah, and Autumnal says, I noticed that we have methods for adding and removing edges in these implementations. Why don't we have methods for adding and removing vertices? Because it just kind of depends on the ADT. Like the particular ADT that we're dealing with just doesn't operate like that, is the short answer. So you could there would be different approaches that could do that. They would have a different ADT with different functions and could be implemented differently, because you got to remember that the ADTs like we look at in this course are not like written in the Bible, right? Like it's there's lots of different ones for lots of different use cases. And even between programming languages that have fairly similar data structures, you'll see some differences between them. So we've talked about the ADT of a graph, our ADT of a graph. We've talked about implementations given that ADT. And now today we're going to be talking on the more algorithmic side about how do you use these things. Or more specifically, we're going to be talking about graph traversal. Because graph traversal is kind of a key part of like why you even use graphs. Because you don't just make graphs to like build them and keep them there. You make them to search them often, which is what I've just said here. I always start this lecture doing what I'm going to like. I wrote this too, I guess. But the kind of few things we're going to talk about are, what does it mean to actually traverse through a graph? And then we're going to look at two key methods of traversal, which are called a BreadthFirst Search and a DepthFirst Search. And then we're going to expand that knowledge a little bit more next week. Well, week 7. Anytime I say next week, I mean week 7. This is a pretty useful part of this course. This knowledge definitely plays into a lot of other things you're going to do in computer science. So I think, there's some parts of trees that you could nope out of, but I would definitely not nope out of this topic. So that question of like, why do we use graphs and why do we find graphs useful? It's because we often want to ask ourselves questions. Now, these are very conceptual questions. These aren't really questions that you might ask in the real world, but questions like, can we remove an edge from this graph and keep it connected? Okay, so think about a real world application of that. I think I might have had some, no I didn't. What are some real world applications of that? Okay, city planning or some kind of grid planning where you want everyone to be connected but to have to build the least number of roads. Is the vertex reachable starting from somewhere else? Same kind of thing. You could build like, flight connections, network maps, road maps. What is the quickest way to get from one node to another? So again, similarly, let's say you're trying to minimize fuel costs for freight or something like that. You could represent flight connections as a graph and try and minimize the amount of the edge cost of getting between places. And is there a minimal spanning tree that links all the vertices? Okay, that also makes sense because if you have like say a whole collection, I think we bring this up later as that's a really good example for like garbage collection and post delivery and stuff is that because you have different kinds of problems, right? Like you have like a standard, maybe you want to fly from A to B and you drive from A to B and you want to do it with the least edges explored. And then you have other problems such as this bottom one with the minimal spanning tree, which is that I want to visit every house in Sydney because I have to pick up their garbage. How do we visit every single vertex like a house while minimizing edge costs? So lots of super, super interesting problems. This is a really, I guess, exciting space. We're often using the phrase search and traversal when it comes to this topic. And there are three, I guess, key ways that we search or traverse. And I don't think this, in my view, I don't think this is often explained super clearly to people when they're trying to understand this topic because they can get mixed up really easily. But if I have like let's just take a standard graph here from the internet. If I have like a very complicated graph like this one, I can really ask three types of questions, and these are written here in the slides. And those three types of questions are, I'm searching for an item to see if it exists. I'm looking for a particular path, that's a series of connections between things, or I'm trying to explore the entire graph. They're kind of like the three key things here. So a searching problem is pretty straightforward. I start here and I'm trying to see if the number 9 exists in the graph. So I just kind of go through it and I'm like, yep, blep, 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 going back here, and then it's like, oh, I found it. So 9's in the graph. The whole job of that particular process is to see if it's there. There's different ways you can navigate around the graph, but you're just trying to, it's like a true or false, like a Boolean thing. Is it in the graph or not? That's like the simplest kind of thing, is just searching whether something's there. The next thing you can do, which is a little bit more complicated, is what we call pathfinding, where you're looking for a number like 9, but once you found it, you want to actually have the path. Like I went from 1 to 2 to 5 to 7 to 9. So it's very similar to searching, except you actually want to keep track of what you did. You want to make sure you know the way you got there. Pathfinding might be a good example. A good example of that might be like Google Maps, right? In terms of say you're using Google Maps and you're trying to get somewhere, Google's going to, for instance, theoretically do a big search of a graph of Sydney, and then it's going to give you the way there. So that's an example of pathfinding. And then the last type of thing is what you would call a full traversal. And a full traversal is where you're interested in actually visiting everything on the graph. You're actually interested in going like exploring all the different nodes. Now this is kind of like a minimal spanning tree thing, like we talked about with like garbage pickup or post people dropping off mail and stuff. So that's one way you're not just interested in going from A to B and finding the way there or checking if there even is a way there. You're interested in exploring the entire graph and building this network and exploring everything. So they're the kind of three different things we can do with a graph. Now, in practice, all three of these things kind of work with the same algorithms. They're all kind of based on the same algorithmic base. And this is where these breadth-first search and depth-first search comes in. But all these different kinds of graph traversal or graph searching is all just a systematic way of exploring edges. It's moving between vertices and exploring edges. often we're focused on a start point and a finish point, but we don't have to be. And the solutions we're going to look at today, they can sometimes be iterative and then they can sometimes be recursive. So there's usually always iterative solutions to this stuff, which I tend to work with more. But there's sometimes recursive solutions that, like trees, can make things even easier. And sometimes, depending on the particular problem we're trying to solve, sometimes we might need to store the path as we explore it, so that we can actually see like what has happened, essentially. Now, I mentioned to you that there are two primary types of traversing a graph. Again, whether you're searching, finding a path, or traversing the whole thing, it doesn't really matter. They're all following the same algorithm. There's just three different reasons you might be using it. The first type is called a depth-first search. Well, there's no first or second. One of the types is called depth-first search, and the other type is called a breadth-first search. And the differences between them are that a depth-first search is focused on going as deep as quickly as possible, and a breadth-first search is focused on going as wide as possible. So if you pay attention to these GIFs here, you'll notice with the depth-first search, it's a bit like a tree search. Like, I mean, these are graphs, of course. There's just graphs without cycles. Notice how a depth-first search actually looks very similar to how you might do a recursive traversal of a tree. It's trying to go down as deep as it can, and then it unwinds, and then it goes back down as deep as it can. So in some ways, a depth-first search is quite similar to what you're used to, and our recursive tree solutions are effectively depth-first searches, in a sense. So go as deep as possible. And you know this from trees. If you have a tree with like a branching factor of 2, binary search tree, and like a height of 20, it's going to go all the way down the left and then start coming back. A breadth-first search in a total opposite way is always trying to explore things like one level at a time. So it's always trying to go down one level at a time. So if you imagine a tree, for instance, that's why we start with trees here. A tree has like a bunch of nodes with different heights. In a tree example, it's kind of like doing everything on level 0, then everything on level 1, then everything on level 2. That's a bit of an oversimplification, but essentially I think we get to it in a sec. I'll leave the formal definition for it now, but we're always trying to expand out, like, if you drop some water on the ground, the water just expands out in all directions perfectly, right? I mean, maybe not perfectly, but it tries to expand out in all directions. All the water doesn't just rush in one direction. It tries to kind of expand itself out. Yep, so print nodes in level order is similar to BreadthFirst Search. Yes, definitely in Lab 4. Matthew says, when you try and go to a new node, check whether that node has been explored and don't explore it if you've already been there. Oh yeah, sorry, yes, and you had the previous comment. Yes, I understand. Diorora says that would become pretty space complex, and by that, Diorora means that it would use quite a lot of memory. Either of these algorithms can use quite a lot of memory. It's really about using the correct one for the job. Now, another conceptual representation of this right here is that both breadth-first search and depth-first search, they do ignore edges when they search, because no matter what type you're using or what you're using it for, you usually keep track of where you've visited previously. So you usually keep track of some kind of like little like set of like, oh, I've been to this vertex, I've been to this vertex, I've been to this vertex, to prevent cycles. Someone asked previously, where was the question? It was, yeah, Diorora says, how do you avoid getting stuck in cycles? You essentially store a list of all the nodes you visited so that as you're expanding out, you don't explore them again. So if you look at a depth-first search up here, the way this one works is that it always tries to go to the smallest letter, but it starts at A and then it goes to it goes to B and then it goes to C and then D and then E, then G, sorry. Like that, it hits a dead end and then it unwinds. It doesn't want to go to A here because it's already visited A, so it keeps unwinding. It doesn't want to go to A or B here because it's already visited that, but it will go to F. Like that. So, and then similarly it'll go to H, and H is probably what it's looking for here. So it does keep track of where it's visited, and a breadth-first search is very similar, because a breadth-first search up here will start at the A, it'll expand out in all directions, so it tries to explore all of its children in one sweep. So it goes, I'm going to explore B, then I'm going to explore C, and explore D, And then you can see as we're expanding out B, C, and D to get their children, we're not exploring C or D here across, right? Like these edges here aren't being explored because they're connected to nodes we've already visited. So there is like a bit of a history. So hopefully this gives you a little quick sense of how these two algorithms essentially branch out. So BreadthFirst searches go wide and depth-first searches go deep. That's the main difference between them. But we're going to start with BreadthFirst Search. Now, I like starting with BreadthFirst Search when I teach this stuff. Some people like starting with depth-first search, but I'll explain later why I like doing this. So conceptually, traversing with a breadth-first search is about starting at a node and then expanding out equally from there. You visit all the neighbors of your vertex that you're at. So if you're at the root node, you visit all your neighbors, and then you visit all your neighbors' neighbors, and then all your neighbors' neighbors' neighbors. So it's kind of like that. It's just expanding out. Now, as I mentioned before, you do keep yourself a visited array, typically, of nodes you visited before. Which I'm just having a look here. So what, I'm just reading the chat. Oh, right, very funny. So what I believe is happening here in this particular diagram is that this visited list isn't really storing a true or false value for whether it's visited. So it's not really like a visited list of Booleans, but what it is it's a visited list that stores where it came from. So it's what we would call sometimes a predecessor list, like what's its predecessor. So as we expand out a breadth-first search here, as we expand to 1, 2, and 5, so 1, 2, and 5, these are all set with a visited value of 0 because that's where we came from. So 1, 2, and 5 came from 0 when we explored it. And then similarly, when we expand out from 2 to 3, because we got to 3 via 2, we mark 3's index here as 2. And then as we again keep expanding, like let me really I'll try and let's take this example here and let's go through it from scratch so you can kind of see how this like algorithm would flow. So firstly, let me just get rid of some of these lines really quickly, or at least make them the right color, and we'll just delete a few things. So I'll give you a sense of how a depth-first search works. And it follows a fairly straightforward kind of pattern of behavior, which is really good. I really like searching graphs because I actually think that the algorithms are really straightforward, and I think the algorithms are listed on this page here. So let's quickly talk about the algorithm, and then we'll go back and look at it because I think the algorithm looks scarier than it is. So breadth-first search, as we kind of mentioned here, can only reasonably be done iteratively. It's very simple. There's no real simple recursive solution for it. And the way that a breadth-first search works functionally is that it uses a queue to essentially figure out what to explore next. So when you're doing a breadth-first search, you're often storing a queue of nodes you have yet to explore, and you're storing a visited list or a predecessor list, whatever you want to call it, of nodes you visited. And they're kind of the two data structures that you use as part of a searching algorithm. And the basic way that breadth-first search works is that you have a queue of numbers vertices you're ready to explore, and while that queue is not empty, you keep reading off it, exploring it, and then add its children to the queue. So that will probably sound really heady to you, but let's try it out. So first thing I'm going to do here is I'm going to create my queue structure as well. And then we'll just get that together. The queues, you don't need to worry about an index because queues don't really have a sense of index, I guess. Whoop, nearly there. This queue's probably too big. Okay. So here's the process you follow. It's extremely straightforward. Firstly, all of your visited lists, say, we'll start. I mean, all of these will be defaulted to -1. I won't fill them in because I'll just have to override them. But like, these are all kind of defaulted to like a -1 or a null or 9,999 or some kind of like value saying infinity. I think on the slides here you saw that -1 was how it kind of started. So this is the default state of all these kind of particular rows. So when we explore a graph via BreadthFirst Search, you always start the same way, which is that you put your root node into the queue. Now remember, the way we insert into a queue is that we insert them in this way and we take them out this way. So this 0 here got kind of slotted into the end and it slid all the way up to the front. Now the way the BreadthFirst Search algorithm works, and maybe I'll just try and write it up here, is it's like, let me make this smaller. So a more condensed version of what's on those slides is that you insert root into queue. You say while queue is not empty, pop off queue, explore children, or pop off queue, add children to queue if the children haven't been visited. That's kind of the really simple, I guess, like algorithm. And you basically just do that until you find the end. So it's like you do that while the queue is not empty and not found. So in this case, let's say that like this particular algorithm, we're looking for the number 9. So 9 is like the number we're looking for in the graph. Maybe it's the number we're trying to find a path to. Maybe we're just trying to check if it's in the graph. It doesn't really matter. So we follow this very straightforward algorithm. We insert the root, which is 0 here, into the queue. And then we're just going to follow this. So this is a very simplified approach, but okay, I've got 0 in my queue. Great. I'm going to pop it off the queue. Done. Now, what's 0's parent? 0 didn't really have a parent, so let's just pretend there's like no parent for 0. So remember, with the visited array, we actually we like store in here what its parent was. We could do this as like a true or false if we wanted to, but in this case, like the visited array is going to say that the node 0, what's its parent? So it doesn't really have a parent, so the first one's a bit weird. So I popped 0 off my queue. Okay, so now I've explored 0 because it's kind of in my visited array here. And then I say, okay, what are the children, or I think someone corrected me, it was like neighbors. What are the neighbors of 0? Well, 0 has 3 neighbors, which is 1, 2, and 5. They're the 3 things that I can connect, via the edges of 0. So I'm going to add those to my queue. But before I add those to my queue, what I'm going to do is I'm going to check if I visited them before. So I look in my visited array here, and there's nothing in there, right? So all these are still -1. So I say, okay, I haven't visited 1, 2, or 5. So that's an important check. So if they haven't been visited, I add them to my queue. So I'm going to add them in numerical order, just for simplicity. So I'll add 1 to my queue, I'll add 2 to my queue, I'll add 1 to my queue, I'll add 2 to my queue, and I'll add 5 to my queue. And then once I add them to the queue, I also need to add them to the visited array because I've visited them now, right? Like they've been neighbors. I've added them to my queue. So we know that the parent of 1 is 0. We know that the parent of 2 is 0, and we know that the parent of 5 is also 0. So that's kind of the only tricky part, I guess, of the whole BreadthFirst Search, which is like, okay, I popped off a node. That's the node I'm exploring, which is 0. And then I simply add the neighbors of that node to my queue if I haven't visited them yet. That's it. And when I add them to my queue, I also mark them as visited here by storing where I got them from. So in this case, they all came from 0. Now here's the cool thing in my view about BreadthFirst Search. It's a really straightforward algorithm, even though it looks complicated, because you just keep doing this over and over again, like over and over again. So I'm just going to follow the exact same procedure. I'm going to pop something off the queue, which is a 1 here. So 1 is now my like node of interest that I'm exploring. So I look at my 1 node. Now what do? you add all of its children to the queue if they haven't been visited. What are its children? We have 0 and 5. They're the two children, but we've kind of visited them already. 5 we just visited, and 0 we is the root node, which we've already kind of technically visited, right? So, I mean, maybe I could just put this one here as 0. It doesn't really matter. So, the algorithm says that I've popped 1 off the queue, and then I add all of the unvisited children to the queue. But all of the children have been visited, so I do nothing. Great, so that's step 2. There's like an iterative approach here. And then the next step is I follow the algorithm again. I haven't found number 9, right? The queue's still full, so I pop something else off the queue. So now we're kind of looking at 2 over here. Okay, cool. Now 2 has 2 children, which is 0 and 3. Now 0's already been visited, but 3 hasn't. Okay, so now I can add 3 to my queue, like this. What do we do whenever we add something to the queue? We also have to update the visited array. So I update it for 3, because that's the node that I just that I'm adding to the queue. Except where did we get 3 from? Where did it come from on its way to 3? It kind of came from 2. Because that's where it just came from. We were just like seeing all the children of 2. So we just keep doing this, and then queue's not empty, so we pop off 5. So 5's our node of interest. 5 has how many children? It has 3, 4, 1, and 6. Okay. But 3's already been explored, 1's already been explored, so the only 2 new nodes we're interested in are 4 and 6. So we're going to add 4 and 6 to our queue, 4 and 6, like this. Because we added 4 and 6 to our queue, we need to fill in their visited. They both came from 5, which is very convenient because that's the node we're exploring, so really easy to tell what that is. They both came from 5, and then great, okay, done. And we keep going. We pop 3 off our queue next. So I'm going to take 3, pop it off my queue. Now what children does 3 have? Children has child 2, 4, and 8. So 2 and 4 have already been visited, so I don't worry about those neighbors. But 8 hasn't. So 8 gets put into my queue. And then I mark 8 here as coming from 3. Like that. Because that's what I just had popped off, So we just keep following this process. Then I pop the next thing off the queue, which is 4. Okay, so 4 is our kind of node of interest that we're popping off now. 4 has 4 children, 3, 5, 7, and 8. Okay, so 3 we've already visited, 5 we've already visited, 8 we've already visited, but 7 we haven't. So 7 goes into the queue now, and the where we got from 7 was 4, because that was the node we popped off. See what I mean? It's just extremely cyclic. You're just doing the same thing over and over again. Then we're going to pop off 6. Like that. Pop off 6. 6 has 1 child, which is 5, but we've already visited 5, so we don't add anything to the queue. Cool. Oh, did I miss one? Oh, no. What did I miss? Where did I miss it? We got to unwind. Oh, God damn it. How early was 5? Crap. Okay. So I screwed up. Oh no. That's okay. This is good because we get more time looking at it. I missed the child. What did I miss? 7. I missed 7 when we were exploring 5. So this would explain also why the result's slightly different here. Very sad. Yeah, just pretend it erased. That's okay. No, I really want to step through this a few times. I know for some of you it's boring, but it's like some people really don't get this algorithm at all. Jackie says, what is stored in the visited array initially? We can't store 0 since that could be a number we're searching for. Generally, you store -1 there, assuming that -1 is not in your graph. Because remember, typically, as I mentioned on Tuesday, the numbers in the graph here often represent an index. They're not like representing a value. So typically, you'll just have indexes 0 through to whatever. And Matthew says, for large graphs, would you keep track of the nodes with a binary search tree instead of an array to speed up searching visited nodes? Not really. I don't think so because, so again, remember that these nodes in the graph are indexed. So these are indices for like the actual vertices. Vertices might have a different kind of value. So because there's like 50 nodes in the graph, you can create an array of 50 and that array is constant lookup, constant time lookup. So the array will be perfectly fine for this. But let me keep stepping through this without my mistake. So we got to here earlier. I've just undone things. Okay. And I'm going to pop off 5. Now, how many children did 5 have? More than I realized, which was 1, 0, 2, 3, 4, and 6. A lot. But 1, 0, 1, and 2, we've already visited. 3, 4, and 6, we haven't. So now we get 3, 4, and... I did it again. 6 and 7. God, I just don't like the number 7. Thank you. Wow, that's funny that that happened like a second time and I nearly didn't pick up on it. So, you know, we add 3, 4, 6, and 7 because those 3, 4, 6, and 7 didn't, like, you know, they haven't been visited yet. So now that they're in the queue, we mark them in the visited array and we mark them from where they came from. Yeah, you're right, 2 wasn't. So we mark them all as 5. Yes. Yeah. Give me a sec. Give me a sec. I've missed something. When I hit undo, I missed a step. Sorry. So let's try it one last time. If I don't get it right this time, you can murder me. Yeah. Someone's picked up on it. I noticed the problem. See, when I undid things, you gotta undo them in the right order. Yeah. So Ricardo says that's why we let computers do this instead. That's absolutely correct. So the only thing I forgot to do here was mark 2 off. So I'm just actually gonna start again. Which I know some of you are like, oh, that's so boring. But honestly, like, there's 400 people in this course, and I guarantee you that there's some sitting around right now going like, what are we doing? This doesn't make any sense. Okay, so let's use another color for good luck. Okay, let's do it. So, how do we start? We always insert the root node into the queue. Great, that's the first thing, and then we start following our iterative algorithm. We take the root node out of the queue. We look at its children, which is 0, 2, and 1, 2, and 5 here. We check if they've been visited before. I'm just going to put the 0 there for 0. We check if 1, 2, and 5 been zeroed before. 1, 2, and 5, no, they haven't been visited before. So we put them into the queue as 1, 2, and 5. We do them in a consistent order. They don't have to go from like lowest alphabet to highest or anything, but they should be consistent. You can go from lowest to highest or highest to lowest. Generally speaking, you should always just go lowest to highest. And because we added them to the queue, we have to add them to our visited list here as 0, 0, and 0, because that's where they all came from. Okay, then we pop off the queue. Done. Take the 1. 1's our like current number of interest. 1 has 2 children, 0 and 5, but again, we've already visited those 2 things. So we don't do anything. We pop 1 off, but we don't do anything with it. Now we're going to pop 2 off. And then 2 has how many children? 2 has 0 and 3. But we've already visited 0, but we haven't visited 3. So 3 gets added to our 3 gets added to our queue now, and 3 came from 2. So we update the visited array with where 3 came from, because this here is referring to node 3. Now we take 5 off the queue. This is where I clicked undo one too many times before and didn't realize. We take 5 off the queue, and 5 has a bunch of children. It has 0, 1, 3, 4, 6, and 7. Okay, so quite a few. 0 has been visited. 1 has been visited. 3 has been visited, because that's here too. 4, 6, and 7 haven't though, so they get added to our queue. 4, 6, and 7. 4, 6, and 7 have all been explored from their kind of parent, 5, so we add 5 to our visited array here. Then we're going to pop off 3. In this case, 3 has how many children? 4, 2, 4, 5, and 8. 2's been visited, 4's been visited, 5's been visited, but 8 hasn't. So we add 8 to the queue, and we put 3 here. Getting all nervous now. I'm kind of like, oh, what have I forgotten now? And then we just keep doing it again. So we take 4. We're going to explore 4 now. 4 has 3, 5, 7, and 8. So 4 has 4 children. 3's been visited, 5's been visited, 7's been visited, 8's been visited. So we don't do anything with 4. So we keep going. We pop 6 off now. Great. 6 has 1 child, which is 5, which has already been visited. Done. So we don't do anything with that. Then we pop 7 off. And when we pop 7 off, 7 has 4 children, 4, 5, 8, and 9. 4, 5, 8, and 9 hasn't been visited, but 9's our answer. So now we're kind of done. Now you could add it to the queue and pop them off if you want, but like we found it as a child in theory, so we're kind of like done now. So we've determined that it's in the graph. And we know that it came from 7. Like that. So this algorithm... Yeah, hooray, we did it, sort of, eventually. This algorithm here helped us figure out that 9's in the graph. Now, if you just are interested in searching, right, so just to stress, if you're just interested in searching, this first one, for whether something exists or not, you still need a visited array to prevent cycles. However, your visited array can just be Booleans. It can just be like true or false, have I visited or not? Okay, so if it's just searching, then you can totally just do a true or false visited array, and you don't need to worry about adding the kind of where it came from or the predecessor. However, if you want to do the second one, which is pathfinding, that means I'm looking for a path to 9. I want to know the specific steps to get to 9. That's when you need like a visited array with the actual predecessor information on it. And the reason for that, I'll show you, and I mean, I'm sure some of you know this already, is that you can actually figure out the path to get to 9 now by reverse engineering the visited array. So we finished at 9, right? And where do we get to 9 from? We got to 9 from 7. Okay, so 7's the next node. Where do we get to 7 from? From 5. Okay, so then we come down here to 5. Where do we get from 5 from? 0. So there's your path. It's from 0 to 5 to 7 to 9. So inside the visited array, when you store the one it came from, is essentially like it's kind of like encoded with the path, essentially, because this is a little bit like a history of all the paths you've been to, or like a parent array, sometimes you get called. So that's why we store more than a true or false there, because if that was a true and false array with just trues and falses, you'd be like, I don't know how I got to 9. I don't. So a couple of questions in the chat were, will this give you the shortest path? The answer is yes. I think what's an important clarifier here is that this graph, we're working with unweighted edges. So all these graphs like have a uniform edge cost, where we assume that every edge traversal is like a cost of 1, like it's a uniform cost. So a standard simple BreadthFirst search will generate the shortest path for you, assuming that all of these edges have a weight of 1, as in they all cost like 1 kilojoule to traverse or something, you know, like $1 to traverse. That's one really important thing about BreadthFirst Search that DepthFirst Search doesn't have. DepthFirst Search does not guarantee you the shortest path. BreadthFirst Search does. So this is the shortest path, or at least tied shortest path. There might be an equivalent shortest path, but this is one of the paths with the lowest cost, you would say. In this graph, obviously, it is the only shortest path, but yeah, just to stress again, that's an important difference, because if we were just searching for the item, we would not need this to be anything but true or false. But if we're searching for a path, then we need to keep track of kind of how we got there, so that when we got there, we're like, it's all right, I kept notes on all this, so I can tell you how we got there. A full graph traversal, you typically can kind of do either, I guess, because a full graph traversal is often just trying to like see what's in there. Pathfinding is probably the most relevant thing. Okay, so that was BreadthFirst Search, sorry. And if you have a look at this algorithm again, it actually starts to make a lot of sense, because we create a visited array, we set all of the values of that visit array to be -1, which I said I just wasn't going to write in because, I'm lazy. We set the visited source to be equal to source. Basically what that is like a bit of an algorithm hack here is that because we're starting at node 0, let's put 0 as like the parent for node 0. That's kind of how we can tell what the starting is. So that's just saying fill the starting node's visited value with itself. Then we add the root node to our queue, which we did in our algorithm. Then, whilst we haven't found the goal, which is 9, and the queue is not empty, let's do our doodly-doo of like, take something off the queue, check if it's the destination, then, for that node, look at all of its neighbors, and anything we haven't visited, mark it as visited, and add it to our queue, and then keep on going like that. And at the very end, if you need to like make a path, this is what this is. This is just some like random pseudocode that's basically like, look at the visitor array and figure out what the path was. Probably the only thing to point out about this algorithm is you notice that this algorithm doesn't stop when one of the children is the goal. It stops once what we popped off the queue is the goal. That's kind of an important detail for later algorithms. I think with a BreadthFirst search, you can kind of get away with so with a BreadthFirst search, you can kind of stop at 1 or 2 points. We popped 7 off the queue, and then we said, oh, 9's a child of 7. Done. We found it. We found the goal. We're done. You could kind of hack around it and do it like that, though a more appropriate way to do this that works for a broader array of algorithms is to actually like go to 7 and say, okay, 7 has 4 children, 4, 5, 8, and 9, but I'm going to put 9 on the queue now, and you don't stop until you actually take 9 off the queue. You don't stop until your goal actually comes off the queue, because then you pop off 8, but 8 has no children that haven't been explored. Do I say BreadthFirst Search? I'm sure I'm not like saying BreadthFirst Search, but I'm probably just saying it really quick and it's sounding like that. Or I'm stupid, one of the two. So you keep going until 9 here is actually popped off. So the more kind of stable, scalable way to deal with this graph searching problem is to only stop once you've popped the goal off the queue, not once you've seen it as a child. Okay? So, but I mean, again, for these simple algorithms, you can kind of do either, but that's something to keep in mind. So that's the algorithm. It looks kind of scarier than it is, but once you understand the flow of things, it's actually a very straightforward process, I think. In terms of complexity of a BreadthFirst search, so the thing is, the complexity of a BreadthFirst search depends on the graph implementation, because some graph implementations are quicker to do certain things. So in this course, we've used the adjacency list as the representation that we're kind of, testing this on. And as you can see here, it's like for an adjacency list, each vertex is visited at most once. So the worst case of a BreadthFirst search is that you have to visit every vertex. And the worst case for a BreadthFirst search is also that you have to visit every edge. So therefore, the actual cost of it is having to visit every vertex and visit every edge, which is v plus e. So the worst case time complexity of a BreadthFirst search in this case is O of v plus e. Which I think, yeah. Remember that this is an unweighted graph. So real searches, as we'll learn about in week 7, can get a little bit more complex than this. Because in a real search, you sometimes have to explore edges you've already explored. So a BreadthFirst search of uniform edge weight is a bit quicker to explore than like a weighted graph. Nayuki says adjacency list is at the most cheap for space. I don't think there's any real way to say what the absolute cheapest for space is when it comes to implementations, because you have to remember again that in terms of space, an adjacency list is really good because it only stores the edges that exist. But you have to remember it's a linked list structure. So with every single edge it stores, it also stores an 8-byte pointer to point to the next item. So essentially the cost of storing an edge here is double. Like double what it would be in like an adjacency matrix. So I would say that, adjacency list representations and array of edges are generally very space efficient for sparse graphs. It depends on a few details. Like if your array of edges thing is literally just 2 vertices indexes, then technically vertice indexes might only be like 4 bytes, and like it's much of a muchness. You could bubble it down if you want to, but doesn't really matter too much. So I really want to talk about this before the break because I don't think there's actually much more to this lecture. But a depth-first search, okay? So let's get this done before the break. Here's the reason I like kind of talking about the iterative method. So this was an iterative method with a breadth-first search because we're using a while loop. There's no recursion, it's all while loops. Depth-first search is about going as deep as possible until you reach a dead end, then unwind and keep going back through nodes. You should intuitively understand this from trees because recursive tree searching is a depth-first search in a way. It kind of decides which way to go, but like a full tree traversal, as opposed to a search for a value, is a depth-first search in a tree. And you can kind of see how this one moves through here. If it's always trying to go to the next lowest index and go as deep as it can, it starts off at 0, it goes to 1 because it's lower, goes to 5 because it's lower, it then goes to its lowest child it hasn't visited, which would be 0, but we visited it, so it goes to 3. 3 has 2, 4, and 8, but we've... well, it goes to 2 here, you can actually see that, right? It goes to 2, and then it goes to 5, and then 6... It goes to 2, and then it goes to 4 and 7, and then it can find 9 pretty quickly. It might go up through like 8 or something. I think the example in the slides, they're searching for 7. The example I did, I was saying let's search for 9. So that's why this one stops at 7. But essentially, it just goes as deep as possible. So it's not trying to expand out all the children. Now, what I like about the iterative solutions between... So I just noticed the tiniest typo suddenly. This code is all right, except this says BFS instead of DFS. And the reason it says BFS is because I copied the algorithm and then I modified it. And the cool thing about that is that the algorithms are nearly identical. So with a depth-first search, the cool thing about it is that you can essentially recycle all of the knowledge you've developed on the iterative solution of a breadth-first search. Whoa. What the hell was that? Oh, sorry, something made a sound on my computer. You can recycle all the knowledge that you've done from a breadth-first search totally, except the difference with a depth-first search is that instead of using a queue, we use a stack. Yeah, stack go burr. So here I'm just going to use a stack instead of a queue. And up here, anytime you see the word queue, I just want you to imagine this written as stack. Okay, so that they should all just be written as stack. Stack, stack, stack. So, but we follow the exact same procedure. We use a visited array. We insert the root into the stack. We pop it off the stack, we explore its children, we do the exact same thing. And it's super interesting watching the behavioral difference here. So what do I do with what's my algorithm? Well, the pseudocode says, okay, well, we start at 0, which is our root node. I set the visited value of 0 to 0. Then I'm going to add 0 to my stack. Now, how do stacks work? You insert them this way and you take them off that way. So they're going to slide down there, but when I take them off, I grab the first value on the right. So I'm going to insert 0 into my stack. Done. Okay, so then I follow the flow. I pop 0 off my stack. Okay, done. And then I add all of 0's children to my stack as well. Now, in this case, just for consistency, well, It's ironic. I'm going to add the nodes in this case in reverse order. So I'm going to add the highest node first into my stack. So 0 has 3 children, which is 1, 2, and 5. So what I'm going to do is I'm going to add 5 to my stack. And then I'm going to add 2 to my stack. And then I'm going to add 1 to my stack like this. Because I added them to my stack, I need to mark their parents as well as 0. Because that's where it came from. So 0, 0, and 0. Okay, now here's the interesting thing. Here's where it all gets interesting. I'm just going to keep following that process. I'm going to pop off my stack the number 1. Okay, so 1 gets popped off the stack. Great. 1 has 2 children, but 0 and 5 have both been visited before. So I don't do anything with that one. Now I'm going to pop 2 off the stack. Okay, so we pop 2 off the stack. Now 2 has 2 children, which is 0 and 3. 0 we've already explored, but 3 we haven't. So I'm going to now put 3 in my stack. And then put 2 here. Like that. Because that's where it came from. Then I'm going to pop 3 off my stack. You notice we're always popping off the most recently inserted things. So I pop 3 off my stack. 3 has 4 children, which is 2, 4, 5, and 8. Okay, but 2 and 5 have already been visited, so the only 2 things I need to put into my stack are 4 and 8, but I'm going to put them in reverse order here. 8 and 4, and then I have to add them to the visited thing. 3 and 3, like that. Okay, and then I'm going to pop off my stack. I'm going to pop off the number 4 from my stack. 4 here has 4 children, 3, 5, 7, 8. 3, 5, and 8 have been explored, but 7 hasn't. So I'm going to add 7 to my stack. Its parent was 4 here. Great. And now I'm going to pop 7 off my stack. And look at its children. It has child 4, 5, 8, and 9. But 4, 5, and 8 have already been visited. So I only need to add 9 to my stack. And then 9 came from 7, because that's the node I just popped off. And then what do? We pop 9 off the stack. And because we popped the goal node off the stack, we say we're done. We do the little party streamer emoji, whatever that looks like. The one that's like, yay, streamers. And then we can get our path as well, because now I go back to 9 and I say, okay, well, 9 here came from 7. 7 came from 4. 4 came from 3. 3 came from 2. And then 2 came from 0. And 0 came from 0, so that must be the start. Like that. So the path that it found was 0, 2, 3, 4, 7, 9. Like that. Was there a reason that I added them in reverse order? No, I just wanted to try something different. Order's a somewhat arbitrary thing with depth and breadth first search. Generally, we will tell you if we want you to explore it in a particular order. Like we'll say, explore add the smallest node to the data structure first. But I mainly did that, yeah, so it kind of felt like we were going through the smallest numbers. Though I think I actually tried to do that because like at a glance, I thought that's what they would have done here, but yeah, I'm not too sure. My brain's too fried to think too much about that. But so a depth first search is just different. But again, the cool thing is that the iterative approach is the identical algorithm, literally identical. The data structure is different. So you're still doing pops and pushes, but it's just the way the data structure handles it. So if you understand depth first search, you understand breadth first search, and those two things. You can make both of them make sense together. You will notice that depth first search did not find the optimal solution. That's just the nature of the algorithm. It's not breadth first search is thorough because it kind of seeps out from the start. Yeah, so the slides didn't say that 2 came from 0. So I'm guessing that the slides would have done, 1 would have been popped off first, and then 5. Didn't we do that? Did I make a mistake? I don't know. I'm not like super confident about if this makes sense. I think what they're doing here is only adding things to... Yeah, it looks like they didn't put 2 or 5 on the stack. Or more specifically, it looks like they didn't add it to the visited. I don't think it's so much they didn't put it on the stack. It looks like that it wasn't added to the visited thing, because what changed our approach here was that when we popped 1 off the stack, we weren't exploring 5 because it was already added to the visited array. That's interesting. I wonder, let's see, a DFS algorithm. Maybe I've gotten something wrong. Let's have a look. See what the internet says about it. What does it do? Start at 0, we add 1, 2, 3 to the stack. It seems to only add the visitor when we pop it off. Oh, that's not good. I'll have to go away and double check that. I don't think there's a big issue with that though. It does produce a different result, but the thing about depth first search generally is that you don't really use depth first search to find the optimal way to get from like A to Z, because it's not an optimal algorithm. The nature of it is that you could get lost in a tangent way down here, and the solution's like just to the right. So it's not really a big deal. Anyway, let me go double check that. I might have a slight detail inconsistent there. I mean, I'm not too worried because I've seen tons of depth first search algorithms looking like what I've just described, but the inconsistency makes me want to figure that out for you all to make sure that you don't have any confusing times when you're looking at things online. Yeah, the only difference structurally here is that trying to see when it actually... I mean, these are the recursive ones which we're about to look at. Okay, speaking of that, let's take a break and then we'll keep talking about the recursive one, which will then hopefully put it in perspective a little bit. So yeah, let's take a break and then we'll talk about the recursive DFS, because you can have a recursive depth first search, but you can't have a recursive breadth first search. So there's a little bit of nuance to that, and then we'll wrap up this lecture talking about the cost analysis. So yeah, take a 5-minute break, and then we'll get stuck back into it. Getting pumped. Getting pumped for 2521. I'm pumped. Boom. Hi, everyone. So, one thing I did over the break was that I had a quick Google because I was kind of losing my mind. I was like, oh my God, did I get something wrong? And I went back to the old lecture slides for this course, and my understanding at a glance, I'll give you the best, I think this explanation satisfies things for me, is that the iterative method for DFS, the one we went through, I think does what I did here, because it's the same method that was used in previous years and stuff, which is the same method I've been teaching in other courses. So I think this is totally fine. I think there's a subtlety though where the depth-first search approach, the recursive approach, explores things slightly differently, as we might see. So what I think this slide is, I think this slide's actually the recursive example of DFS, and I think what I did was the iterative example. Speaking of recursive example though, we did our iterative one here, which is great. Very simple. It's a stack, not a queue. But the recursive algorithm is actually even simpler. And it actually makes a lot of sense to me now why this is happening. But what I've got here is a few different kind of DFS algorithms, but they're all largely the same. And the way a DFS algorithm works for recursion is that if you just look at the first one, which is a full traversal where you're not looking for paths, you're not trying to check if you found the goal or anything, you're just literally trying to touch every node in the graph, is that you start off and you say, I want to depth first search the graph G from my root node. And then what it does is it adds your node, the root node, to a visited list, and then it looks at all your children, all the neighbors, and if your neighbor's not been visited, it then starts recursively calling depth first search on that. And this actually makes sense to me now because the addition of the neighbor to the visited list only happens when it's, in a technical sense, taken off the stack. So the behavior of the visited list appears to be slightly different for the recursive example. So I think I've answered my question before. I think this is very hard to explain to you and just be like, here's all the explanations around how this works, because recursion's kind of like that. You just have to trace it out. But structurally, I want you to just think about it as like, if we just had a, let me find some. If we just had, for instance, an algorithm like this one, without the visited check, like this would technically be a tree traversal, right? In the sense that like a tree traversal, normally when we say things, we're like, we're like tree search, T or something. And then we say like, tree search, T left, and then T right. What is T left and T right? It's like all the neighbors of a parent, right? All the outbound edges, the children, whatever. So a depth first search on a graph is actually identical to a search on a tree, where you're literally saying take a node and recursively explore its children, which in this case we call neighbors. The only difference is that because a graph has cycles in it, unlike a tree, we need this visited list. So it's really just a standard tree recursion, except we have the visited list part of it that actually prevents cycles. So these two lines here of, adding the node we've just explored to a visited list, and then only exploring nodes that haven't been visited, is essentially a form of what you call cycle checking. So the DFS algorithm is very concise. You don't need a stack. You don't need a data structure. You can actually just use the... you're kind of using the stack on the program, right? You're not using a stack data structure that you've created. You're just like using a stack that you've... using the stack itself that your program runs on in the operating system. So that's like what a full traversal is. If you're trying to do path finding or path checking, then again, I'm not going to go through this in much depth, but it's very similar to a depth first search, except you're obviously going to have to keep track of the visited lists. You're probably going to have to generate a path at the end and all of that. Yeah, so path check here is what I refer to as a search, which is saying, given a starting node and an ending node, tell me if there is a path between those two things. And pathfinding is saying, from a start node and an end node, tell me what the path is between those two things. And then a full traversal is just saying, look at everything. Just go to every node for me. Just touch every node in the graph, please. And it goes, okay. They're the main differences. So Waleed says, should we know both recursive and iterative DFS? Yes, I guess everything we teach in the course you should know, though personally I like writing iterative solutions. Ask your tutors what they think in terms of what they think is easiest. I like iterative solutions because I only have to think of one thing, and then I can apply it for both BFS and DFS, and I find the procedure very straightforward, and I hate debugging recursive things. Though if you're just trying to do a full graph traversal on a DFS, this is really simple too. Like, this is dead set simple. So sometimes if recursion makes my code simpler and I can get it done quicker, I find it kind of attractive, I guess. The only thing to point out, of course, though, is that I want to say that recursions, you have to be tricky with them because they really blow out the stack. Like, we kind of learned this in the week 2 or whatever it was, where like Because remember, when you're doing recursion, it's basically just like a whole bunch of like stack frames being added. Like here's your main program, and then you recurse this side, which recurses this side, which recurses this side, and it's just like a whole bunch of like functions that are getting stacked on top of each other until you unwind them. But I don't really know how much more memory intense that is than keeping a stack, because this, like, a recursive approach only gets troublesome when your graph is huge. But I guess like a stack would get huge as well, maybe. I don't know. I wouldn't be a major concern for me, because I don't think an iterative DFS is going to be painfully better. I don't know what that meant. But yeah, I I think recursion's worth knowing how to do. Yeah, it depends how fat the graph is. That's very true. I think it's definitely worth knowing how to do this. It's actually not that crazy hard, but my point is, like, off the top of my head, I would feel comfortable writing an iterative DFS, and my preference is just iterative because I, again, only have to know one algorithm, which is, what I would call a graph search via a data structure algorithm. And the nature of how you search just depends on whether that data structure is a queue or whether that data structure is a stack. Forgot to hit unrecord, re-record, bugger. That's okay. Damn it. Okay. Cost analysis of a DFS is exactly the same. V plus E, because a full traversal in the worst case is still touching every edge and node. You've just done it in a very different order. So yes, the cost is the same. I mentioned this a few times. DFS does not guarantee an optimal solution. We've touched on that. And this is just one last little comparison of how like a BFS and a DFS might find different spanning trees, equal minimal spanning trees. And in this case here, this is what a full traversal is. It's you trying to touch every vertex in the graph. So that's what a full traversal is. And all full traversals produce spanning trees. Then it's just a question whether it's a minimal spanning tree or not. And then, yeah, if you could provide some feedback, that would be great. And we can move on to the next lecture in our last 40 minutes, which is pretty light. We hopefully won't run out of time. So yeah, that would be great if you could give some feedback. Thank you.